Hello, my name is Austin Bladden. I'm part of Group 7, and our reverse engineering project was the HTC M8. We're going to go through a brief feature overview. It is a 2013 era smartphone with 2.5 GHz quad-core 801 Snapdragon by Qualcomm, with 2 GB of integrated RAM and 32 GB of flash storage. It also has an array of sensors, and as well as regular 4G connectivity, as well as AVG and AC Wi-Fi support. Okay, this is the teardown process in which we first got to this point, and we were kind of lost because this metal sheathing we assumed was originally soldered to the board, but upon further inspection it was actually mechanically coupled via these little clamps. We removed it, and this is what we found underneath, including the Snapdragon, RAM, and so on. And we're going to give it to Pranav.
Hello everyone, my name is Pranav and I will be talking about the first level packaging involved in the HTC M8. So the modules that we considered to study so as to better understand the first level packaging involved in this system are, first of all, the Snapdragon 801, which refers to the main processor unit of the phone, which happens to be a package-on-package configuration. I'll talk about that a bit later. The second one is a SanDisk SDIN8DE 432 gigs, which is the memory device. The Qualcomm PM8921 refers to the power management unit of the phone. And the Avago Power Amp IC is an integrated circuit which performs the function of a power amplifier, as it is obvious. To start with, let's talk about the Snapdragon first. So a bit of information about Snapdragon. The processor device of this phone is a package-on-package system, which means that there is a vertical combination, or it's created in a vertical collection of two modules, one being the LPDA RAM module on the top, and the next being the Snapdragon module on the bottom. And the Snapdragon, as you can see in this picture, is actually a system-on-chip package, which means that there are a host of modules, subsections, which are actually packed together on one platform and are interconnected in order to perform the functions as they are required to. Now, when we decapsulated the entire processor package using concentrated HTC, it exposed the LPDA RAM module, which is on top, and it also showed that this module is in fact connected to the substrate using wire bonds. So we used optical microscopy to zoom in to the wire bonds and understood that the wire bonds are in fact made of gold. And zooming in a bit further showed that there are ball bonds on top over here, and that's the ball bond pad. And at the bottom are the wedge bonds. It's a ball wedge configuration. Now, if you look at the top unit, now, in addition to the optical microscopy, we also did X-ray microscopy, which showed that inside this red box region of the ball grid array, there are actually really tiny solder bonds, which are very fine, which give the impression that they are actually C4 bumps, which imply that there's actually a flip chip configuration going on here. And just to talk a little bit about the system-on-chip package, which is a Snapdragon. The three major units which are found on the Snapdragon are in fact the CPU, which is a Qualcomm Cray 400. There's a CPU architecture, which is of 32-bit. And of course the GPU, which is a Qualcomm Adreno 330. Now for the memory device, this was again studied under the X-ray microscope, and it of course showed the ball grid array pattern, but going through literature online, we also figured out that this is in fact a thin profile fine pitch BGA with a 153 ball BGA package. And because we couldn't find a lot of information about SanDisk online, a lot of it is confidential, we are basically telling you what we found. Third is the Qualcomm power management device, which is the PM8921. And in this, under the X-ray microscope, we noticed that this uses wire bonds. Now, of course, there are no leads coming out of the packaging, and we're suspecting a chip scale package over here. But one question that we wanted to think of was why wire bonds are being used over flip chip. And given the fact that this is in fact one of the smaller active components of the PCB, we figured that so as to cut costs, wire bonds were chosen as an interconnect over flip chip. And to finish off, I'm going to talk about the Avago power amplifier unit, which again is a very small module of the PCB, of the size of just about 7 by 5 millimeters. And that is a multi-band, multi-mode power amplifier. Of course, the X-ray image, again, as you can see clearly, it reveals an wire bond pattern. And the question that we asked over here is, it seems to be aluminum wire bonds instead of gold. And we would estimate the same reason of cost cutting, given that it's a really small module, that aluminum wire bonds are chosen over gold.
Alright, again, my name is Austin Ladden. I'm going to be walking you through the second level packaging of our HTC M8. Okay, this is a functional device block diagram of our Snapdragon 801 device. This is what, more or less, what all Snapdragon phones who use this processor are going to look like. And we're going to dive into the LPDA Snapdragon 801 package mentioned before. We have the Qualcomm ENME690, which is the official name of the Snapdragon 801. It is a fine ball grid array system on chip. It has a 0.40 and 0.5 millimeter pitch, 0.20 millimeter pad diameter, and then the LPDA FA164A2PM is 16 gigabit, 2 gigabyte dual inline channel mobile LPDDR3 SD RAM, which is the RAM for the processor. It is 216 ball package on package fine ball grid array, which is actually this whole part, with 0.5 millimeter pitch and 0.325 millimeter pad diameter. Okay, so the idea behind the stacking the RAM on top of the processor was to reduce the connection length between the two units, allowing for low voltage operation and reduced signal decay. Here, as Pranav mentioned, there's really tiny C4 bumps. The medium-sized balls here would be the solder balls connecting the PCB to the Qualcomm Snapdragon lower module, and on top of that are the 216 ball grid array that connects the RAM to the Snapdragon itself. Okay, and then next we have the SanDisk iNAND embedded flash, which is SDIN 8D E432G, which serves as the device internal storage. It is an electronic multimedia card supporting 4.51 with 0.5 millimeter pitch and 0.35 millimeter pad diameter, shown here in X-ray, and that would be this one here. Okay, additional components include the Avago power amplifier, which is small outline no lead. It is important to note that the majority of the chips and components on this PCB are of ball grid array type, including this Qualcomm WCN 3680 Wi-Fi integrated circuit. We also have surface-mounted passives, right here being resistors, capacitors, inductors, and we also have surface-mounted flexible printed circuit connectors. That would be these, connecting major components, including the daughter board and baseboard, to the motherboard itself. Okay, peripheral device interconnections. Most of the main components are connected via a flexible printed circuit. There are a few wired connections that would be shown here and here via tiny coaxial wires. Main components include the daughter board, which is this blue board here, which houses all system cameras, a SIM card reader, vibrator motor, earpiece speaker, and limited I/O devices. When I say limited I/O devices, I am referring to push button devices such as the power button, volume rocker, and things like the infrared emitter. Active components on the daughter board also include the NFC controller, barometric pressure sensor, among other sensors, and the dynamic antenna matching tuner. And the baseboard, which this bit here, is also connected to the motherboard via a flexible printed circuit. It houses a micro USB charging port, 3.5 millimeter audio jack, and system microphone. One thing I found interesting about the flexible printed circuit on this phone in particular was that between the motherboard and the screen itself, there were surface-mounted passive devices on the ribbon itself, which freed up potentially space on the motherboard. And now we're going to move on to printed circuit board with Beihan.
Hi, this is Beihan Zhao, and I'm doing the printed circuit board and the thermal management for this HTC M8. For the printed circuit board, I'm basically doing the identification of the layers and the laminates, and based on coarse length and some images taken by SEM. So based on our observation, we found 10 copper layers, including suspected power layer, ground layers, and a signal layer. We also found some micro layers, including some plated through holes. And of course, we identified the CCM and PPG in the board. As we know, that the printed circuit board is under the second level packaging, and it has a function of the mechanical performance improvement and the electrical connection and all this stuff for the entire performance. So first we come to the CCL analysis. So through the textbook we found, we have like a list of all the materials metrics in the laminate of the CCL of the PCB board. That it is basically the thermal performance improving, mechanical performance improving, and the CTE adjust. And we have a fine SEM picture of the CCL. So this is the copper layer, this is the fiber, this is the glass fiber, and this is the filler, this is the fabric, which is a yard of the fiber. And this is for the reinforcement of the polymer matrix. So this is the identification of each layer. So from observation, we find 10 copper layers if we count it. And I suspect that this should be the solar mask because this one is a cross surface under the wire bonder BGA. And this layer like forms the CCL. And this is, I suspect this is the PPG because in the SEM picture it has a deeper color, and because it's like partially cured in the B stage, and it's the like bottom copper layer. Okay, let's come to the breakthrough holes. This one is taken from the substrate that is like on the top of the PCB board. This is the top layer of the PCB board. This is a breakthrough hole in the substrate. This is the core. This is the PPG. If you like zoom in it, you can find this color is deeper. And in this SEM picture, due to the slicing mistake, it's partly damaged, but we can still find the copper layers and the blind wire over there, buried wire over there, and the solder boards and the PTH over there. Then we come to the thermal management. So for thermal exploration, the main topic is based on the thermal consideration in the electronic packaging and the thermal expression based on the modeling. So there are 4 main considerations in thermal management, which is heat spreader. We observe like a layer of copper foil, and the thermal wires, which could be everywhere in the packaging, especially like the one mentioned in class, the cavity down wire bond BGA, it has thermal wires in the substrate. And I suspect this could be, the wire bond BGA could be cavity down in one of the chips, and this could be suspected thermal wires. So to validate my assumption and the efficiency of the thermal improvement, I built a CAD model and input it to ANSYS. This is all the dimensions I mentioned. This is some details of my design, and by building the model and input to ANSYS, we can run the simulation. So this is the simulation result get from the ANSYS, and we also, because like Professor Han said in the course, the experiment result, everybody would believe it, but you know the uncertainty. The modeling, only you believe it because the others think it is not accurate. So we need to compare each other. So after we tear down, I did a experimental setup, which means that I put the motherboard here using the laser to hit the central part. I have some like coating area to absorb the laser heat, which is here. So by using the similar initial conditions and boundary conditions, we build the simulation and we run the and we observe the experimental results. The range of temperature is accordingly similar. But we also have so many uncertainties, which is listed here, like the materials uncertainty and those ignored passive components. So after validating our modeling and the simulation results, we can see the efficiency of the heat spreader of the copper layer. So after putting the copper layer on the top of the existing modeling, the results decrease 5 degrees for the simulation results. So which means the spreader is actually using as thermal thermal pad for that, and we can do other modelings based on the considerations mentioned before. So one of the possible improvements is the heatsink under the PCB board. I read this from an article published by the Fujitsu from Japan. They want to develop a super thin and fluid cooling heatsink for the mobile device applications. And another thing that could be the optimization for the thermal performance is that we can use the TEC. In one of the papers that published by Professor Beihan in the University of Maryland, they have done the experimental setup like this, and compared to the packages that without the TEC cooling or the sport cooling, the one with TEC cooling can have 19 degrees better performance in thermal. And there are some, so in conclusion, we have thermal pad, some possible thermal vias, and we also may have some conductive materials through the motherboard. And the future step could be based on chip level and consider more about the interconnections. I have built some initial models for the future consideration, but I have not finished it based on the limited time. And there are some difficulties to go through it because most of the information is confidential, and we need more professional experimental devices for that.
Okay, my name is Pascal, and I will be covering the reliability portion for our project. This is the outline for my section. And first of all, we're going to define what reliability is and apply that definition to the HTC M8. Then we're going to talk about electronic packaging, go into general causes of failure and failure mechanisms in electronics. Then we're going to look at the reliability for the main processor chip for the HTC, and we'll finish with qualification testing methods used by industry and maybe other alternatives. So reliability is defined as the ability for a system to perform as advertised in a specific operating environment for a specified time. And if we were to apply those three parameters to the HTC phone, first of all, we have the performance of the HTC, which we know those cool features that Austin talked about in the beginning of the presentation. However, for this here, we're going to focus on the expected performance of the electronic packaging of the motherboard and the failure modes and mechanisms that we encounter. As far as the expected life, it is an accepted value that by industry that cell phones have a life cycle of 5 years, 4.7 years. The HTC, however, offers a warranty for 1 year, which I thought was interesting. As far as end user environment characteristics, this is something that's very proprietary because the end user environment characteristics determine the safety margins that you need to put into your design, and it's been difficult to find the documents that were used by HTC. However, I was able to find some general industry estimates, and here we have a table from JEDEC where we see that, again, the 5 years life cycle, power on cycles 20 per day, and relative humidity 10 to 100. Electronic packaging this is one of the stuff that we cover in the class, it encompasses the technology required to protect and cool active silicon chips and interconnect them and distribute their signals to the components, the surrounding components. So causes of failure in electronic packaging can stem from design flaws, manufacturing process defects, or end user environment or device operation that is outside of what the system is designed for. And as far as failure mechanisms, we're going to divide them into two categories: the overstress type, which leads to an immediate failure, and the latent type, which is a degradation of parameters in the system that eventually leads to an unacceptable performance of the system or a total failure of the system. So here we have the HTC M8 main processor, which is a Snapdragon, and it is a package on package, which here we have the package for the RAM, and here we have the system on chip for the processor itself, the Snapdragon. And as far as little characteristics, the RAM is wire bonded and it has 216 balls, and operating temperature range is from negative 30 degrees C to 85 degrees C. Snapdragon, the data is more guarded. So I was able to find some information for the 800 series, not the 801 series, and here we have the dimensions here also. And these are, we have 990 pins under the Snapdragon, which are the fine pins that Pranav was referring to during his presentation. So the causes of failure, like you said, you can have 3 vectors. You have design flaws, manufacturing defects, or excess end user environment. And what I've done is that I've divided them into first level, second level, and printed circuit board. And what I wanted to point out is that, for example, in first level, for design flaws, we definitely do not want stress concentrators, because the stress concentrators will amplify any form of load or stress that is put on the system. Also, as far as manufacturing processes, we see that the first level packaging is sensitive to voids, contamination, and presence of moisture that will lead to popcorning in the next step of the second level. Now we're going into the failure mechanism, and the first failure mechanism type that we want to talk about is the overstress. This is failure mechanisms that lead to immediate failure, and we have 3 vectors through which overstress type failures can happen. We have mechanical, electrical, and thermal, and I want to point out for example, that the thermal, we have a glass transition that affects mainly the PCB, and that is something that we definitely want to avoid. We don't want the PCB to go from a ductile-ish type of behavior to a brittle type behavior, which then can impact systems performance. Latent type failures, like we said, are failures that accumulate over time. And again, here I have the type of failures for each of the vectors. We have the chemical one that's added with corrosion, and I have the packaging areas that are mostly impacted. I want to point out electrical migration, which is something that happens at all 3 levels, and it is due to the flow of electrons and impinging their momentum into metal ions. And the gain momentum by the metal ions causes them to move and creates voids. So the void can be seen in vias, for example, in PCBs, and eventually the void can lead to an open circuit once the whole metal is cut. So here is the main processor again. This is the Snapdragon, the combination of Snapdragon and Elpida. And this is some concerns we should have as far as reliability and performance. So first of all, it requires known good dies, because before you invest into the process in the assembly of the package on package, you want to make sure that all your dies work appropriately. Also, we have some inhomogeneity in the system, and by that, what I mean, for example, I have this here to illustrate. So you have your package on package, and this is a top view of the Snapdragon, which is a system on chip. We have a CPU, remember it's a system on chip, so you have various chips here, and the large CPU is where you would have the hotspot. So that is inhomogeneity that you have in how this whole package perform. And as you can see also on that paper, when that heat, when it transfers to the ELP, the RAM that is on top, there's enough insulation with the EMC and this substrate here that you only see a change of temperature of 3 degrees C. There's also warpage, which is something that is major for stacking package on packages or 3D integration. And warpage happens when you have a CTE mismatch between the 2 packages. So here, what we're seeing here is that the ELP, the RAM, has a CTE that is not the same as what the Snapdragon package has, and hence we have a warping of ELPida package. So we want to talk about qualification testing. All the reliability concepts that we talked about, eventually they have to be qualified from the early beginnings of semiconductor industry and electronic packaging. They've used standards. Those standards come from various associations like JEDEC or AEC for automobiles. And one of the advantages of the standards is that it allows a comparison of the components across different suppliers. So if a component is made in Japan and another one is made in the United States, if they're both qualified with the same standard, then you can compare their performance and know what to expect. Another advantage is that the standards come with their qualification plans pre-written as far as sample size and whatnot, so there's very little work needed in order to implement. As far as the cons for the standards, the requirements are rigid and they can be too severe. By too severe, I mean that you can have a design that maybe cannot handle the prescribed levels of overstress and thus lead in massive failures. Another way that industry is starting to look at qualification testing is knowledge-based methods, which is basically it's a failure mechanism driven instead of being stress driven, and it's tailored to the system that you're trying to qualify. The advantage of this is that it's more accurate for predicting the lifetime of your system. It allows you to maybe have smaller margins in your design because you are more aware of how your system is going to be used. However, it requires a lot of parameters such as complex documents that are difficult to obtain. It requires an understanding of all the failure mechanism of your system. And if, for example, you skip one, you didn't realize that you were going to have one, then you can have a flaw in your system that will never be addressed. And that concludes at this time our presentation. Thank you for your time and hope you enjoyed it.